Welcome to lesson 5, the final lesson from chapter 6, Trigonometric Functions. Today we're going to look at something slightly different. We're going to leave those Pythagorean identities and we're going to look at inverse trig functions. Now, you've been using inverse trig functions for quite a while, but we're going to do some analysis on the function itself, its graph and its behavior, okay? And that will apply for each of the inverses of sine, cos and tan. Now, some notation appears straight away. So the inverse trig functions we denote as arcsin. Now, that arcsin simply represents the inverse sine function which you use on your calculator, which appears as sine with a -1 as a superscript. Okay, so that's what that is. And then similarly, arccos would be cos to the power -1. And it would take you from a value on the y-axis of your sine or cos graph to a particular angle. Okay, and also arctan, which of course would be tan to the power -1. So there'll be more about that later. Please just pause the video and have a go at the warm-up questions. We're going to look quite a lot at domain and range in this lesson. Okay, so please pause the video, try the warm-up questions. Okay, and let's go through the solutions. Right, for worked example 1, I don't just want to give you the answer and just move on. I'd like to take some time here to talk through these ideas about mappings and functions because they are very important in mathematics. What I've done is for each of these mappings, I've provided you with a diagram as an example, and we're going to see why these may or may not be functions and any other properties that they may have. So in the first diagram, we'll start in the top left. We can see that we've got a one-to-one mapping. It's a mapping at the moment. The first one in that hyphenated phrase represents the domain. So it means one unique element from that domain. And one unique element from that domain must map to an element in the range. Now, for it to be a function, it doesn't matter what the element is in the range that it maps to, as long as every element in the domain is accounted for, i.e. every element has somewhere to go. Now, in this instance, if I choose any unique element in that domain, so let's say I'll just pick a point here. So that's a number in my domain. We can see from the graph that it maps to one unique value in the range, okay? And this is true for any element in the domain. If I pick an element over here, it maps to a unique, and I'm using that word carefully, it maps to a unique element in the range. Now, if this happens, whereby every unique element in the domain maps to a unique element in the range, this is what we call a one-to-one mapping, okay? And one-to-one mappings are functions. I'm just going to explain the function again. So if a function is a mapping, but it will map every element in the domain to an element in the range. Okay, now you don't have to have a situation where every element in the range has had an element in the domain mapped to it. That's a special type of function which we actually call a surjection, which we're not going to talk about in this course. But the important phrase here, or the important word, is the fact that every element in the domain has to go somewhere. Okay, it doesn't matter where. So this is what we call a function, and it's a one-to-one mapping. Okay, now one-to-one mappings have unique properties, as we've discovered. So if it's a one-to-one, it also has what we call an inverse function, because the inverse function will switch the domain and range around, and you will still have that one-to-one relationship. Okay, so we can just make a note of that. So this has an inverse. Oh, I've spelled inverse wrong. Has an inverse. Okay, because the inverse will also be one-to-one. In the inverse, these two words will just swap round. Okay, so it will still say one-to-one as the domain and range switch. All right, now if we move on to the top right, we've got a one-to-many mapping there. Now, as I've mentioned previously, if we take any element in the domain represented by the word one at the front, then if we look at the range, then let's see what happens. If I take a unique element in the domain, so let's start with something here, perhaps. Now, this unique element in the domain can go here, but it could also map to this point down here. Now, this means that this is a one-to-many, okay? Each unique element in the domain maps to more than one element in the range. So this is a different type of mapping. Now, the question is this mapping a function or not? Now, those of you who will remember from lessons, we have a little phrase for this. If you have one too many, I'm not condoning this, if you have one too many, then you can't function, is what we say. So this is not a function. Now, the reason why is it breaks the definition. The definition is broken because every element in the domain, it doesn't map to a single element in the range. It maps to more than one. Okay, so this cannot be a function. So let's make a note of that. So this is not a function because it doesn't fit the definition. Okay, every element in the domain goes to more than one unique element in the range. So it can't be a function. Now then, moving on to the many-to-one, if we take any element in the domain, so again, I'll just highlight the domain again. So the domain here corresponds to the many part of this hyphenated phrase. And then we've also got the range here as well. So this is suggesting that many elements from the domain must map to one unique element in the range. Well, let's have a look. So if I take a unique element from the domain, okay, there's the mapping. So it only maps to one particular value. That's good. But I could take an element over here, which maps to the same element in the range. Now that's okay because the function, remember, every element in the domain goes to one particular value, okay? It doesn't matter that they're the same value as long as each element in the domain goes to one specific value. So this is a function, okay? So we can say this is a function. All right. Now, the last one we've got to look at is the many-to-many. Now, if you've followed what we've done so far, this is an amalgamation of the many-to-one and the one-to-many. So you'll probably be suspecting that this won't be a function simply because you've got many in the range, which doesn't work as a function, and you'd be right in thinking that. But we'll go through it anyway. So if I put the domain on here, which corresponds to the first many in that word, and then I put the range on here. So it looks like we're in the crosshairs, doesn't it? If I pick any unique element in the domain, so I'll start in roughly the same place. Okay. If it was just that would be fine. It would be one-to-one. But we can see from this instance, we've got, it's definitely one-to-many, isn't it? Okay. but also I can take the same or a different element over here, and that also maps to many values. So it's a many to many. This is not a function because it breaks the definition. So this is not a function. So out of the mappings we've looked at, the only ones that are functions are the one-to-one, okay, and the many-to-one. Now, if you have the luxury of having the graphs in front of you, as we do here, we can also use something called a vertical line test to see if something's a function or not. Now, I'll show you what I mean. If I'm going to put a vertical line on here on the diagram. So if I take this vertical line, I'm just going to put it on the first function. Oh, that wasn't what I wanted to do. Let's do a nice straight vertical line, like so. So a vertical straight line, so it's an x equals line, if you like, x equals some value. Now, the vertical line test, it runs like this. If you take the vertical line and put it over your graph and just move it along like so, if that vertical line intersects your graph at only one position, okay, then it has passed the vertical line test and it is a function. So you can see that wherever I put this vertical line, it's only cutting the red graph at one specific place. So this has passed the vertical line test and it is a function. Now, this is actually a one-to-one function because it would also pass what we call the horizontal line test. Okay, but if we're just testing for this being a function, the vertical line test will do. If we move on to the second diagram, okay, you'll notice that if I put the vertical line over the second graph, it's going to intersect at two places, apart from there, of course. So apart from when x equals 0, it looks like it's intersecting at two places, and that will continue on in that vein. Now, this has failed the vertical line test, so this means it isn't a function. And again, if I go to the third diagram and just move the straight line across, it's only intersecting once at any point. Okay, so it has passed the vertical line test. And without really going into too much detail, the fourth diagram is obviously going to fail the vertical line test. Now, if we just mention the horizontal line test, the third graph, in fact, let's put that on there. So we'll put a horizontal line on as well. So the first graph will pass the horizontal line test as well, and the vertical line test. That means it's one-to-one. The second diagram, the top right, has already failed the vertical line test, so it can't be a function. But notice that the third diagram, although it is a function, it does in fact fail the horizontal line test. So it means it's not a one-to-one function, but it is a many-to-one function. Okay, so that's just another test you can do. Now then, regarding inverses, which we mentioned earlier, we know that the first diagram, which is a one-to-one mapping, it does have an inverse. We've stated that here. Okay, but the question is, does the other function, the many-to-one, have an inverse function? Well, those of you who remember what we did on functions will know that this is not the case. If I switch the domain and range around, which is what happens when you find an inverse function, notice that the inverse function would be a one-to-many. And we know that one-to-many here can't be a function. So that's why the only way you can get an inverse function is if your mapping is one-to-one. Okay, so we can make a note of that. Only this has an inverse. Okay, so we've said quite a bit about functions and mappings there. Just have that sort of the forefront of your mind when we're talking about what we're going to be doing in today's lesson. Okay, so in contrast, this is going to be very quick. For question 2, we simply have to sketch y equals sine x in this interval. Okay, so it's something you know very well, but we're going to use this later on in the lesson, and we're going to state the range as well. So sine x, if you're not familiar with this, just put some values in, but you'll know that it has its maximum at pi over 2 and 1, and it's going to look something like this, passing through 0, and something like that. That's not too bad. And the range is pretty clear. If you just look at the range of values of x that it's, sorry, beg your pardon, the range of values of y that it spans, well, it's anything between -1 and 1 inclusive. So we can write that down. Okay, so that was pretty straightforward. All right, and for questions 3 and 4, we again have to sketch the graphs of y equals cos x, which you're familiar with, and y equals tan x, for 2 different domains, for 0 to pi, as you can see here, and in the case of tan x, so 0 to pi, sorry, and in the case of y equals tan x from -pi over 2 to pi over 2. So I've sketched the graph of cosine. Just be careful for this domain here. Just be careful with your sketch. Make sure you don't draw a full period of cosine, of course, because remember, cosine is 0 when x is pi over 2. And we can state the range as well. So if you just write that at the bottom, we can see that just like sine, if we have a domain of 0 to pi, we get the full range possible, which is, of course, from -1 up to 1. Notice if that domain was restricted between 0 and pi over 2, perhaps the range would also be affected. It would have a range of 0 to 1. Okay, so you can play around with restricting the domain and the effect on the range that follows from that. So that's cosine. Now for tan, I'd like you to be as accurate as possible with this sketch. If you're familiar with the tan graph, there is an asymptote. There's asymptotic behavior at -pi over 2 and pi over 2. But when we have a range quite limited between just 0 and, beg your pardon, between -1 and 1 like that, as you can see on the diagram, it does restrict some degree how flexible you can be with your sketch. Now, what I mean is, if you're showing asymptotic behavior like this, and don't do this on your sketch, but maybe something like that, wouldn't be quite right, simply because if you just put in a value, let's say halfway between 0 and pi over 2 is, of course, pi over 4. And if you find the tan of pi over 4, you do, of course, get 1. Okay, so just so it fits on this diagram, just be aware of that. So it wouldn't necessarily look like an asymptotic graph, but you would see the trend. It's going to go down here, and then it's going to get closer and closer to that asymptote -pi over 2. Okay, but in the same way, where you have -pi over 4, and if you read off, you'll get -1 there as well. All right, so just to be aware of that now, and I've given the game away here. If you're stating the range, now the range is dependent on the domain, isn't it? Okay, now for the diagram, you don't really see this, but if you're using a domain from -pi over 2 to pi over 2, then tan is not defined at either of those values. But if we do not include those values, then any real number is possible. So the range, although it doesn't look like it on the diagram, is all real numbers. Okay, so I hope that's clear, and I think we're ready to start the lesson now. Right, on the screen in front of you, we have a GeoGebra document, and it shows y equals sine x. We're going to just talk about the graph of y equals sine x for a few minutes, just before we start filling in the notes. And there's a reason for this. If you look at the the domain here, we could say this is any real number, all right? But we're limited on the screen. So it's going from around negative 7 pi over 12 to around 11 pi over 12, as you can see on the screen. So this is the domain that's visible. Okay, the grey curve is, of course, y equals sine x. Now, if you look at the range, I've divided the range up rather sort of unusually. I've used the same pi over 12 multiples as in the domain. And there's a reason for this, which we'll see shortly. But we can identify certain key values on here because we know that if I substitute in pi over 2, we get the maximum value of 1. So that tells me I can read off the value of 1 as being round about here. So I'm just going to put that on. So that's the maximum. So it's just slightly less than pi over 3. Okay, on in my y direction. And similarly for negative pi over 2, which is over here, I've got the minimum value, which is just a bit greater than negative pi over 3, which is of course there. So negative 1 would be round about there. So there we can see the range pretty clearly. Now, we're going to use something that we saw in the warm-up. We're going to apply the horizontal line test to this graph. So I'm just going to get rid of those bits there. If I just put a horizontal line on the board, we can start the test. What did that horizontal line test tell us? Well, we're not doing the vertical line test. The vertical line test, remember, will tell us whether we had a function. And I've just noticed that's a little bit wonky. Let's try again. Yeah, so the vertical line test would tell us whether we had a function or not. The horizontal line test would tell us whether our function was 1-to-1. So if this curve passes the horizontal line test, it would be a 1-to-1 mapping. Okay, and we know about 1-to-1 mappings. They have inverse functions. They're functions themselves and their inverse exists. So if we have a look at this particular curve, I'm going to drag this horizontal line down. We can see straight away that we've failed the horizontal line test. Now, if this was all real numbers for our domain, it would fail infinitely because there would be an infinite point of intersection between this line and the curve y equals sine x. But at the moment, we've got 2 points of intersection, which is enough. It's one more than we need to fail the test. So we failed the horizontal line test. Now, the ramifications of that are that we now have a many-to-one mapping. So this is a many-to-one mapping. Now, is it a function? Well, it's still a function, yes, but it's not a 1-to-1. Okay, it's a many-to-one. We can just see this as well without using the horizontal line and just going back to the definition of a function. Remember, a function maps a particular value or from the domain, or any or every particular value, I should say, to a specific value in the range. And if we just apply that idea, we can use this as a good point here where the line is intersecting the curve. So if my unique value is here where my dot is, and I read off, I get a value just somewhere above pi over 6. Okay, so that means that that particular value that I've just chosen has a unique value or a particular value in the range, which is good. Now, if I chose the value over here, somewhere between 3 pi over 4 and 5 pi over 6, that would have the same value, okay, in the range. Now, that's okay. But we know that I can do the same. I can take any particular element from my domain, and it's going to go to one particular number somewhere in the range, okay? Doesn't really matter which one it is. It can be the same as the value that another number is mapped to. It doesn't really matter as long as it goes to one particular value. Okay, this is a function in essence. So this is a function. Now the question is, does this function have an inverse? Well, I've already said this. No, because it failed the horizontal line test. Okay, it has to be a one-to-one mapping for it to be a function that possesses an inverse. And we said already, it doesn't have an inverse because if I find the inverse function, these domains and ranges will swap. And that means that the inverse function, I'll use the word function loosely there, the inverse function would have a one-to-many mapping. And we know that one-to-many mappings are not functions. So what we need to do is we need some way of forcing this sine graph to become one-to-one. I really, really want to have an inverse function for sine. That's my goal. So what can we do? Well, we can play a few games with the domain. If we can restrict the domain in a particular way so that it forces the function with the restricted domain to be one-to-one, then we can talk about an inverse function. And that's exactly what we're going to do. And in the warm-up, you've already done this. We restricted the domain, as you can see here in the top left, from negative pi over 2 to pi over 2. So let's have a look at what this does. I'm just going to overlay that graph there. Now, there we go. I'm going to get rid of the sine graph. So we've now restricted the domain from negative pi over 2 to pi over 2. Now, notice what happens if I apply the horizontal line test. So I'm just going to get rid of this. I was a bit too overzealous with the erasing there. I do want to keep that line. Okay, so let's apply the horizontal line test. Now I've restricted my domain. We have one point of intersection all the way down. So by restricting that domain, we now have a one-to-one mapping. We can now talk about an inverse. Okay, now the question is, what does the inverse look like? Well, we don't really need to know much about it other than we can see with a little bit of a revision of what we've done on functions previously, we can see that we can sketch the graph pretty easily. Now, if you remember from the work we did on inverse functions, if I plot the line y equals x, which I've just done there, and we can remove that horizontal line now. The inverse function is a reflection of your curve in that line. Okay, so we can actually sketch this inverse really, really accurately using this diagram. So let's have a go. So let's take some key points. Well, we've got the point pi over 2 and beg your pardon, we've got the coordinates pi over 2, 1, okay, as the maximum. Now, in the inverse function, those coordinates will swap over. So that means that 1 will map to the point pi over 2. Well, we know where 1 is roughly. It's just a little bit less than pi over 3. So I can indicate this on my x-axis now. So it's going to be about here. So that's where 1 is. And I know that my coordinate is going to switch around. So that's going to map to pi over 2, which is about there. So let's have a go at sketching this curve. So I can do the first bit. I'll do it in purple. So it's going to come right the way down here and it's going to meet sort of there. So I've had a good go at that. So that's the first half. Now we can apply the same idea to the bottom half. And the negative pi over 2 is not quite on the screen, but that's okay. So do the same thing again. Let's put negative 1 on the x-axis. So there it is. And it's going to map just right to the bottom of the screen. So about here, which you probably just can't see, but never mind. So about there. Okay, and then if we continue the curve that I've started to draw, it's going to come down here and it's going to arc away, and it's going to look something like that. Okay, so let's see what we've got. I'm just going to sort of strip everything else away now, so we'll see what we've got left. Well, we'll get rid of the y equals x line. We'll get rid of the original function. So this is the inverse of y equals sine x. And this is what we call y equals arc sine x. And you can see the range and domain in front of us. Oh, I've just realized I've just undone my sketch. Yes, so we call this arc sine x, and you can see that the domain of arc sine x is the range of our restricted sine x. So the domain now runs from -1 up to 1, and the range runs from -pi/2 all the way up to pi/2, which is exactly how inverse functions behave. So we can now apply that, and we can fill in our notes, and we can do the same thing for the inverse of cos and the inverse of tan. Right, I've added the graph y equals arc sine x onto the diagram. We'll just label that, and we'll just talk a little bit about its properties. So remember, we mentioned about having to restrict the domain for sine x in order to produce this inverse function. We now have a domain because it's the inverse, it's the opposite of the original function, so it's now spanning between -1 and 1, as you can see here. I mean, I've already been through this on the GeoGebra page, and the range is now -pi/2 to pi/2. So it's just a straight swap of the domain and range, which is that property of inverse functions. A couple of other things. Notice the graph still behaves a bit like y equals x along here. That's to be understandable, really, because it's a mirror image in the graph of y equals x. And if you look at as the graph approaches 1 and -1, it becomes more and more vertical, so that when you get to the point 1 pi/2, the gradient would be infinite, essentially. So that's the arc sine x graph. Now, remember, of course, another way to say that would be that this is the inverse sine function. So it's the graph of this, and similarly we can apply the same principles to cos and tan to produce the sketches. Now, without talking about the horizontal line test, let's see if we can deduce from the warm-up sketches of cos and tan what the inverse function will look like. Well, let's use the sine graph as a basic starting point. Now, I'm just going to, over the top of this, I'm just going to do a little sketch of what you came up with in the warm-up. So the sine curve, essentially, for this instance, looks a bit like this. So it runs between, as we've said, pi/2 here, and -pi/2 on this side. And it's just a crude sketch, of course, and then -1 and then 1 for the range. And if you compare that to the sketch we've got, well, yeah, it's a swap, isn't it? But if you sort of tilt your head, it's hard to explain this, or if you've got the paper in front of you, just maybe rotate it so that the pi/2 and -pi/2 are running horizontally. You can see that if you rotate your page, it just looks like the sine graph, but running backwards, essentially. All right. Now, you've still got, if you follow that rationale, you've still got the point pi/2 1 So from pi over 2 to 1 running along there, if you rotate the page, okay? But it's just that you're going in the positive direction to the left rather than to the right. Now, if we can think of it in the same way for the cosine graph, well, we know that the cosine graph starts at 1, okay? And when I say starts at 1, I mean on the y-axis. So the first coordinate of the cosine graph that is of any importance is that point 0, 1, isn't it? Now, if the domain and range are switched, this point is now going to become 1, 0. So that's clearly going to be an important point on the arccos graph. So I'm going to label that. So that's going to be down here. Another important point on the cosine graph was where it crosses the x-axis. So that would be at pi over 2 and 0. Now, remember, the inverse function, these switch around. So that would be 0 pi over 2. Would be another important point, which is, of course, here. And for this domain, or, well, this range, if you like, running from 0 to pi, in this instance, it looks like we're going to have another important point at -1 pi. And we can see why, because on the cosine graph, at the point pi is where the graph is at its minimum. All right, so if we switch those around for the inverse function, that's going to be -1 pi, which is right in the top left corner. So this is a good point now to sort of tilt your head and try and imagine how the cosine graph would run in the opposite direction. Well, if I'm starting at 0, 1, I'm just tilting my head here just to try and get this right. If I'm starting at 0, 1, it's going to be going vertical, then it's going to drop down to 0 here, and then back up like that. Okay, so that looks like what the arccos graph is going to be. So let's label this. So this is y equals arccos of x. And without going into as much detail as with the previous sketch, we have that slightly different domain this time. Well, we have the same domain, I should say, but for the cos graph, we restricted the domain to 0 to pi, and that forces the curve to become 1 to 1. Okay, it's not the same as the sine graph, because cosine is a 90-degree shift or a pi over 2 shift of the sine graph, isn't it? So it's a slightly different restriction in the domain to create that 1 to 1 mapping that you need in order to have an inverse function. I hope that makes sense. Simply because if we used, I'll just go over here just to explain that in a bit more detail. If we go back over to the arcsine graph, and if I just sort of superimpose the cosine curve on top of it, well, the cosine curve would look like this on the arcsine domain. So it would go like that, and then it would also at -pi over 2 cut the x-axis. Now you'll notice straight away that is not a function. Okay, it fails the vertical line test because it's a one-to-many. Okay, and if you have one-to-many, remember, you're not a function, or you can't function. All right, so we'll get rid of that. So that's why we have to restrict the domain in a slightly different way. Now, moving on to the tan curve, it's the same restriction as sine. So we just have to tilt our heads again and think, how does the tan graph behave? Well, if it's easier, we could add a couple of extra points on here. We know that at pi over 4, if you take the tan of pi over 4, you get 1. So that's going to maybe play an important part. And similarly, if you take the tan of -pi over 4, should be around here, you'd get -1. All right. Now, we've got to obviously swap. I was talking about the domain and range for tan there. If these are swapped, then we've got to sort of tilt our heads and draw it backwards, which is kind of hard to do. But it behaves a bit like y equals x in the same way that sine does. So it's going to look a bit like the arcsine graph around here, but it's going to have the asymptotic behavior like that, and then it's going to go something like that. Okay, so that's going to be the arctan graph. And just bear in mind, of course, that this graph is going to continue all the way down here, like so, until it gets to just above -pi/2, but never quite gets there. So it has asymptotic behavior. So we have to be careful about stating the domain and range for this. Well, the domain is fixed, so I can't do anything about that. It's between -1 and 1, and the range is going to be between -pi/4 and pi/4. But if it was a slightly wider domain, which I can't fit on here, which I'm just going to draw on here, like so, the arctan graph would look something like this. Okay, so it would be more like that, and you would have an horizontal asymptotes there and there at -pi/2 and pi/2. Okay, so just be aware of that. It just doesn't appear that way from the sketch. All right, but in reality, the domain for arctan, you can have any number you like for the domain, but your range is always restricted between -pi/2 and pi/2. It just doesn't appear that way from the sketch that you've got in front of you. For the arccos graph, your domain is restricted. So x has to be between -1 and 1, because that's the range of cos. But your domain is going to run between 0 and pi inclusive. And back to the sine graph, your domain is the same as cosine. All right. And then the range is going to be between -pi/2 and pi/2. If you're not convinced, try this on Desmos or GeoGebra, see for yourself, zoom in and out, and just try and convince yourself that these are indeed the domains and ranges, and that the sketches do actually look like this. Now, here we have what I'm calling a useful identity, useful in the fact that it will be useful in one of the worked examples, and it's also, it could be useful in an exam for a similar kind of example, which we'll look at later. So the question we've got here is it's a transformation issue, isn't it? We've got to get from the dotted line, beg your pardon, we've got to get from the solid line to the dotted line. So the solid line, which is the graph y equals cos x, with the limited domain, of course. So limited in the same way as the domain was limited to create the inverse function arccos. So it's limited from to 0 up to pi. So that's the solid curve y equals cos x. Okay, and then we need to map this curve onto this dotted curve, which I'll highlight in yellow, which is another familiar curve y equals sine x. So the question is, how do we do it? Well, at this point, I'd like you to pause the video and have a go yourself, and then we'll look at how this is done. Okay, so you maybe have had a go at this, maybe just check and verify it on GeoGebra if you haven't done so, or Desmos. Now, we've got a couple of options here. on first glance. Now, the first option might be if we take the green curve, which is where we're starting from as our starting point. One thing we could perhaps do is to reflect in the y-axis like so. All right, so that's a possibility. Let's just jot that down. So reflect in the y-axis. Okay, and then once you've done that, you might be able to see that if I translate horizontally to the right by pi over 2, I get the sine graph, which, well, I've almost got it. It depends on how good my drawing is, of course. All right, so it looks like we've got a horizontal translation as well. So perhaps we could translate by pi over 2 in that direction. Okay, I know it's shorthand, it's crude, but it gets the point across. So that might be one way we could do it. Another way we could do it, perhaps, is if we take our curve that we've got already, I'll do these ones in red, and if we translate by pi over 2, but this time we do it to the left. So I'm just going to draw this on so you can see. Just show you the translation again. So if I start here and then I translate by pi over 2 to the left. So if I write that down, so you could translate by pi over 2 in the other direction, so it's going to the left, and then you can see we've got another reflection in the y-axis, haven't we? So if I reflect in the y-axis like that, we get the dotted line. So if I reflect in the y-axis, we should get the graph y equals sine x. Now, there's a problem, isn't there? There's a lack of consistency. We've got the reflection is the same, but the translations are different, which can't be the case, really. You'd be applying different rules depending on whether you do it translation first or translation second. So I think we can agree that there's two transformations, but surely there must be a fixed way of doing this. Well, there is. And if you do a cursory search of Google, as I've done here, you'll see, if I just erase this stuff so we can see what it says, there is an order of transformations, which we have met before. And I might do a separate video just explaining why this order of transformations is the way it is. But we have horizontal shifts first, and then any kind of horizontal stretches or compressions second. So we have to do the translation in the x direction first, according to this, as it states very clearly here. Okay, so if we do that and go back to the document, we're forced to use this second approach here. So we're going to go for, let's get rid of that. We're going to go for this approach, which I'm just going to highlight. Right, so how does this manifest in terms of the actual function? What will this look like mathematically? We can describe it, but we've got to do it. So what I'm going to do first of all, just partition that. So we're going to say let f of x equal cos x. So that's the parent function. Okay, with a caveat, the cos x with the limited domain, but I won't mention that. Now, if we want to translate by pi over 2 to the left, you'll remember from transformations that we're going to have, it's the inside opposite rule, isn't it? So you would think that we would be subtracting pi over 2, as in fact, we're going to be adding pi over 2. So inside the function, we're going to be doing x plus pi over 2. Okay, and in the function itself, that's going to be cos of x plus pi over 2. Hope you can read that. Now then, that's the first transformation. The second transformation we reflect in the y-axis. Now, that means that we have to change the sign of the x input. Okay, and what I mean is we change the sign of this part. Okay, so it becomes negative x. So this will be the next step. So the final function, so we're going to have f of what will become negative x plus pi over 2, okay, is equal to the cosine of, again, negative x plus pi over 2, like so. Now that's the full transformation. So what this means is that the final part that we've got here on the bottom right, this is the final curve after the two transformations have been performed. So this must be equal to or identical to sine x for these domains. So let's do that. So let's write that down. So therefore, sine x is the same as, identical to, the cosine of, I'm just going to change the order, so that's going to be pi over 2 subtract x. Okay, so that's one way of looking at it. With the restricted domain, so obviously the domain changes, doesn't it? As we change the position of the curve after the first transformation, when we do the translation to the left, the domain instantly changes. It's reduced by pi over 2. So it would be from negative pi over 2 to pi over 2. So the domain is also transformed at each stage. Okay, so that's the useful identity. Make that look really important. I would put it in a box or highlight it or something, because we'll be revisiting this later. Oh, and just before I forget, notice the domain here as well for this identity. So the domain is valid between negative pi over 2 for x and pi over 2. So it's not just acute angles here, okay? It's the negative acute, if that makes sense. So I hope that's all right. And yes, we're going to apply this shortly. So far, we've met the inverse trig function graphs and a new identity. And for the first worked example, we're going to find some missing angles in radians. Now, to use the inverse trig functions, there's something that we have to be really cognizant of all the way through this, and that is the domain of the inverse trig function, and most importantly, the range. Now, we've already met the arcsine graph. You'll be able to see this on your page in front of you, but I'm just going to sketch it again in the space. So the arcsine graph, just very, very simply, has a domain from -1 up to 1. And it has a range from negative pi over 2 to pi over 2. Remember, that is the restricted domain of sine that enables the function to have an inverse. It has to be 1 to 1. And then just sort of tilting your head, and we'll put the origin on there as well, actually. Tilting your head, we should be able to sketch the sine function. We know it has a maximum at pi over 2, 1, and a minimum at negative pi over 2, -1. So the sine graph is going to look something like this. The arcsine graph, I should say. Now, in terms of the question we've got in front of us, we've got to find the arcsine of this particular value, which is -√3 over 2. Now, there's a lot of information locked in that. The first thing I'd like to look at is where this would appear on our graph. Now, this is in the domain, of course, now. So if we read off roughly where that value is, it's just a little bit less or a bit greater than -1, about 0.87 or -0.87. So it's about here. So by reading off the graph, we can see quite clearly, I'll just indicate on there where it is. So that's -√3 over 2, it's got a negative value. So it's a negative acute angle, if you like. So we know a little bit about the answer already. So we know the answer is somewhere between negative pi over 2 and 0. Okay, and perhaps I shouldn't use x because that confuses us with the domain. I think I will use theta for our angle. Okay. Now I've specified a possible label for this angle, theta. We could also write this question in a slightly more familiar way. So if I know the arcsine is negative root 3 over 2, then clearly I could just state that theta would be equal to the arcsine. In other words, sine theta must be equal to negative root 3 over 2. So what if I asked, or what if we were asked just to solve that equation? Well, that wouldn't be too much trouble, would it, to find the angle theta? We could actually think of it in those terms if we wanted to, but what we have to do is, like I said earlier, be very, very mindful of the domain and range of the arcsine function. Okay, so let's consider this. Suppose sine theta, I'll just write it up here again. Sine theta is equal to negative root 3 over 2. But remember that our theta is restricted. It has to be between negative pi over 2 and pi over 2. Okay, because that's where the arcsine graph range is valid. Now, if we do that, we can find a principal angle. Now, remember, for the principal angle, we ignore the negative sign completely, and we're going to let the cast diagram deal with the negative sign. So we're just going to find the inverse sine of root 3 over 2. So I'll do that. I'm just going to finish this. So theta will equal the inverse sine of root 3 over 2. Now, this theta is not the answer, of course. This is the principal angle theta. Okay. So at this point, we're going to get our calculator out. And this time, I'm going to be conscious of the question asking for the angle in radians. So I'm going to make sure my angle is in radians. So let's go to the setup. Okay, so shift menu or shift setup, if you like. Select option 2 and option 2 again. Now my calculator is in radians. Okay, as you can see on the display right here. Now, we do the inverse sine of root 3 over 2. So I'll do that. So shift sine, that's the same as arcsine, of course. The square root of 3, just come out of that, divide by 2, and we'll get an answer in terms of pi. Hopefully, yes, we do. So that's going to be pi over 3. So I'll write that down. So theta is going to equal pi over 3. Okay, 60 degrees in old money. Now then, and I'll just write that as radians. Now then, if you look at the diagram that we drew for the arcsine graph, you can see that this can't possibly be the correct answer. We already stipulated that the answer has to be somewhere between negative pi over 2 and 0. So this is where the cast diagram comes in. So if I draw the cast diagram now on here, we can use that and we can actually see that both the cast diagram and the sketch of the arcsine graph do coincide. Now, what we need to be aware of is when we use the cast diagram, we move anti-clockwise in the positive direction from 0. And I'm going to do the cast diagram in radians now. That means that if I move if I move clockwise, I'm going to be moving in the negative direction. So at this position here, I'm going to be at negative pi over 2, which is negative 90. And in this position, I'm going to be at pi over 2. Now, at this point, this is where we've got to be mindful of the domain and range. The arcsin function is only valid between negative pi over 2 and pi over 2. So that means that the sine quadrant and the tan quadrant are not valid whatsoever. So we're only using the right-hand half of the cast diagram to do this. Okay, so we put our principal angle where where sine is negative. Okay, remember earlier on that we said we're going to find the angle. We're going to find the angle theta where the value is negative √3 over 2. So if we have two quadrants to choose from, the only quadrant that would possibly be valid is, of course, the C quadrant where cosine is positive. Okay, so we put the angle on there, which I'll do now. So this is going to be pi over 3. And because we're starting at 0 and moving in the negative direction, this tells us conclusively that theta must equal negative pi over 3. And that is the solution. And it is the only solution to this. Now, if you want to check this on your calculator, you can. Just to try that again. Negative √3 divided by 2. Okay, we get the negative pi over 3. So both the calculator, the cast diagram, and the sketch are all in agreement. What you need to make sure, though, is when you're doing the inverse sine or the inverse cos or the inverse tan, you need to be mindful of the range, okay? The range of the function, arcsine, arccos, and arctan. You can only work within that range because that is the only range where the inverse function is valid. Now, for part B, we have to take the sine of that angle. Well, if we take the sine of the angle, I can do this directly on, on the calculator again. So if I just take the sine of my answer, we'll notice we get the value back. So the question is, why is that? Well, it should be pretty obvious, really. This is an inverse operation, isn't it? So, sorry, I beg your pardon, these are inverse functions. So if I take the sine of an arcsine here, it's like saying take the sine of a sine to the -1 of negative √3 over 2. So in other words, the sine and the inverse sine, because they are inverse functions, they just cancel each other out. In other words, it's like taking an e to the natural log of x or the natural log of e to the x, something like that. The functions basically undo what the previous function's done, and you're returned to negative √3 over 2. Okay, so I hope that makes sense. So just to finish that off, that's going to equal just exactly the same, negative √3 over 2. So worked example 2, we're given an inverse trig equation, arc cos x equals k. Just to remind you what this means in an alternative way of writing it. So because to the -1 of x equals k, and we're given this range of values of k from 0 to pi over 2. It's a good idea at this point to sketch the graph of arc cos x. If you've got it in front of you, that's fine, but just as an exercise, let's sketch it with its domain from -1 up to 1, because that, of course, is the range of cos, and the range and domain obviously swap when we have inverse functions. The range of arc cos, of course, is different to arc sine. It's going to go from 0 up to pi, because that's how it was restricted to form that one-to-one function so that the inverse function can exist. And at the halfway point, we're going to have pi over 2, like so. And if you tilt your head and work backwards, I'm just going to draw this in red. Remember, the cosine function begins at 0, 1. So the first coordinate, if we swap those around, is going to be 1, 0. The cosine function crosses the x-axis at pi over 2. So this is where the arccos function will cross the y-axis. And therefore, I think we've got enough information now to start penning this in. So that's your arccos graph. Okay, so we'll just indicate that. So that's going to be y equals arccos. In fact, I've not left myself enough room there. Let me just rewrite that. So y equals arccos of x with the double C in the middle. And just indicate the x and the y axes, which I've not labeled either. It's not a good habit to get into. Now, that's there in front of us. Now, just so we're clear, in this question, we're told that the arc cos x is equal to k. Now, k can only take values between 0 and pi over 2. Now, what might be clearer is if I just go over to this y-axis, this is clearly going to be the k-axis, isn't it? So I'm going to relabel that as the k-axis. Okay, because it's the output that I get when I do the arc cos of some input x. Now, if the k value is only going to run between 0 and pi over 2 as its range of values, now that obviously puts a limitation on the domain, doesn't it? Okay, now if that's true, the domain can only be between 0 and 1 inclusive. Okay, so that's important. And that's answered the question for us, because if this is the case, then the x values can only be between 0 and 1. And the sketch of the graph has just sort of crystallized that for us, hasn't it? We can see it in front of our eyes. To get that range, we'd only have to put in between 0 and 1. So I hope that's okay. Now, and that answer should go there, but I thought it looked better writing it next to the k values. So the next job is we have to express in terms of x sine k and tan k. So it looks like sink and tank, doesn't it? How do we do this? Okay, well, let's have a look at some of the properties. We've got arc cos of x equals k. Let's start with that. So for part B, I'm just going to write that out again. Arc cos of x equals k. We know that x can only be between 0 and 1 at this point as well. And we also know that we can rewrite this as cos to the power -1, or inverse cos of x equals k. Now then, one of the properties we've not really applied too much at the moment is what would happen if we take the cosine of both sides of this equation. So if I do the cosine of cos to the -1 of x, that must equal the cosine of k. Okay, so we apply the cosine function to both sides of this equation. Now, if as we mentioned with sine and sine to the -1, they are inverse functions and they cancel each other out. One function undoes whatever the other function performs. So we now have the situation where we have x on the left is equal to cos of k. All right, so that's another way to phrase exactly the same statement. Why is this important? Well, we have a sine k to find, and we know that cos k is equal to x. Right. Well, how can we think of cosine of k? Remember, k is an acute angle. I'm just going to refresh your memory here. K is an acute angle and it's stipulated here. We know what cos K is, it's X. So how do we usually find out what sine K would be and tan K? Well, we could draw a triangle. Let's do that. So I'm going to draw a right angle triangle. And the beauty of this is because we have that restriction on K as being acute between 0 and pi over 2, perhaps slightly more than acute, that means that we can use a right angle triangle really effectively and we get the answer directly from this. We don't have to worry about the cast diagram and all possible angles between 0 and 2 pi or beyond. Now then, if we label this angle, I'm going to put my K angle at the bottom here, like so. I don't need to label the other angle. And we know that cos K is equal to X. So what I can do is, because trigonometry is a ratio, it's defined by ratios, I can say, well, if cos K is X, well, what that means is cos K is just X over 1. Okay, where X would be the adjacent side down here and 1 would be the hypotenuse. So that's the relationship, isn't it? So clearly from that right angle triangle, I could look at that right angle triangle and just say, well, clearly cos of K in this situation is just going to be X over 1, which is just X. So it seems to fit. K is obviously an acute angle because it's inside a right angle triangle, obeying the laws of geometry there. So we're in business. Now, we can find sine K really easily now using a bit of Pythagoras. Okay, so let's make a note. So using Pythagoras, or Pythagoras' theorem, it's a shorthand for theorem there, we can get the opposite side, no problem. So we know the opposite side is just going to be the square root of the hypotenuse squared, which is just 1 squared, which is 1, subtract the adjacent side squared. So in other words, the opposite is just going to be the square root of 1 subtract x squared. Okay, and we can just indicate that on the diagram. So this side here is the square root of 1 subtract x squared. Now, using that information, if I just go up to this side of the board here to answer part B, part 1, I can see that sine K is just going to be the opposite over the hypotenuse, which is simply just going to be 1 subtract x squared. Now, I've used the right angle triangle there. Now, you might be thinking, that looks as though I could have used a different technique here. Well, yes, of course you could. I mean, what you could use is sine squared plus cos squared is identical to 1. Yeah? But what we need to be mindful of is that K is an acute angle. Okay? Now, knowing that K is an acute angle, there's absolutely no ambiguity whatsoever between the fact that X is going to be a positive number. In fact, it's between 0 and 1, isn't it? Because we stated that earlier here. So that's a positive number. And 1, the hypotenuse is obviously positive, which forces the opposite side to be positive. Now, if you use the identity, there might be some uncertainty about whether to take the positive or the negative square root. Okay, but seeing it sort of physically in front of you, K is an acute angle, X is positive, the hypotenuse is positive because they're measurements of the sides. The opposite side must be positive as well. It just removes that ambiguity. I hope that's okay. And the other benefit of using the right angle triangle is we can now get tan K really easily as well. So to get tan K, we can just write this down. Well, you can get tan K easily using identities, but I just like using diagrams, as you probably are aware. So tan k is going to be the opposite over the adjacent, which is going to be the square root of 1 subtract x squared over x, which of course is just sine k over cos k. And you'll notice that that is also a positive value as well. Okay, so I think that concludes worked example 2. All right, before I go on to the final example, because it's so important, I just want to show this transformation, or this combination of transformations to get from the cos x function defined between 0 and pi, as you can see on your screen, to the sine x. Now, if you'll notice, this function f is just representative of cos x. If I translate by pi over 2 to the left, so in other words, use the translation vector negative pi over 2, 0, we get the function g, as you can see here. And this is performing, obviously, the transformations in order, so it's the translation horizontally first. And then once I've performed that transformation, I can then perform a reflection, which will give me the sine function. Now, the sine function, which obviously is valid. Now, this is the important part, between negative pi over 2 and pi over 2, which matches the arccos range. Okay, now there are other identities that you can use that map sine onto cosine and vice versa, but this is the one that maps a cosine with a restricted domain from 0 to pi onto a sine wave with restricted domain from negative pi over 2 to pi over 2, i.e. transformations which are valid for the arccos and arcsine functions. So I just wanted to show you that again, because this is really important. So in this final worked example, this is, this has featured on exams in the past. It's a really interesting question, and we are going to utilize that identity. I'm going to write it down first, so we can see from that demonstration and from the work we did previously that sine, I'll just get rid of that, sorry, the sine of x, okay, valid between negative pi over 2 and pi over 2, is exactly the same as the two transformations that were applied to the cosine wave. Okay, and the cosine wave was translated and reflected, and okay, this is what we just discovered. Now then, just so you're aware as well, you can see this identity play out in another, perhaps a more intuitive way, rather than using transformations of waves. So I'll just draw this right angle triangle here. Okay, and I'm going to label the bottom left hand angle x. Now, it doesn't take much angle reasoning to realize that the other missing angle in the right angle triangle is obviously going to be pi over 2 subtract x, okay, because the angle sum has to be pi, dealing in radians, of course. Now, you'll notice very quickly that if I take the sine of the angle x, so the sine would be the opposite side, which is here, divided by the hypotenuse, which is there. So I'll write that down. It also coincides with the cosine. Remember, the cosine being the adjacent over the hypotenuse of pi over 2 subtract x. So you can see the same relationship, and that's always true. So that's an identity. And that's looking at the acute case for acute angle x and acute angle pi over 2 subtract x. All right, so I think we've made a good case for this. Now, how does this apply in this question? Well, it allows us to answer quite a difficult question in just a few steps. So we're given some piece of information here. We're told that u equals arcsine x. Okay, let's write that down. So u is equal to arcsine of x. Now, in the same way when you write down a logarithm, as we did earlier in the course, there's another piece of information we can write down. We automatically know that, well, I'll just write it out in a different way so it's a bit more obvious. So i.e. u is equal to the inverse sine of x. So consequently, I can write that in a different way. So I'll go into another color as well. We can say that sine of u must equal x. So that's rather useful. But we need to bring in this arccos because I have to add them together. Now, where on earth are we going to get an arccos from in this situation? Well, this is where this identity comes into its own. All right, so we've got this identity at our disposal, ready to use. So let's use it. And valid specifically for arccos and arcsine functions, remember. Now, we know that sine u equals x, so I can write this identity in terms of u. So using the identity, I can say that sine of u must be exactly the same as the cosine of pi over 2 subtract u. All right, so that's the relationship. Now, because I have this additional information from earlier, I also know that sine u is equal to x. Okay, so I can now replace the sine u with x. So therefore, x is identical to the cosine of pi over 2 subtract u. We still don't have an arccos, but if I apply the inverse cosine function to both sides of this, the arccos will reveal itself. So we're going to have cos to the negative 1 of x is identical to cos to the negative 1, so it's applying that function to both sides of this identity, of the cosine of pi over 2 subtract u. I'm using the cos to negative 1 so you can see clearly that it's an inverse function. Now, on the right-hand side, beg your pardon, on the left-hand side, I should say, this cos to negative 1 of x is what we call arccos x. So I can now bring in that. So therefore, arccos x is identical to, or equal to, I should say, because we've called the u a specific thing, haven't we? So I should drop the identity now. And now we have the inverse cos of the cosine. These two functions annihilate each other. In other words, they're inverse to each other, so they undo what each other does. So they have no net effect whatsoever. So we're left with pi over 2 subtract u on the right-hand side. All right. Now, we know what u is, okay? We saw it earlier. It was defined, it was given to us. U is equal to arcsine x. So let's sub in arcsine x. So arccos x is equal to pi over 2 subtract arcsine x. And a little bit of rearranging will prove our result. So arccos x plus arcsine x is equal to pi over 2. So it might be interesting to see what this actually implies. So if we add the arccos and the arcsine functions together, we're essentially going to get pi over 2 every single time. Now, I can show you this if I just select a straight line tool here. The arcsine is the brown curve F, and the arccos is the green curve G. Now, if I take just some particular point here, let's say here, and I'm just going to measure the distance between y equals 0 and the curve. So that's the arcsine function, and then I'm going to measure the same distance again. I'll use the green. So if we take that value, so that's going to be the value of arcsine. I beg your pardon, arccos. So the green line is arccos. I'm just going to move them now. So two different measurements. Now, if I just stack them on top of each other like this, hopefully they fit. So you can see I've not done an amazing job, but they sum to pi over 2. Now I could do that for any 2 points, and you'll see at this point here where the 2 curves intersect, right here, it's the midpoint. It's at pi over 4, and clearly those distances, if you add them together, would give you a pi over 2. Now you might be thinking, well, what about the left-hand side? Well, this is the key. Those are negative measurements on the arcsine graph. So if I just show you what I mean there, if I take the distance from 0, let's say from this point here, and we'll measure the distance from y equals 0 to y equals arcsine x, that's about there. And if I do the same thing but for the arccos function, so I'm going to measure that distance. Now, because the orange line is a negative distance, I have to subtract that from that cosine distance, the arccos distance. And if I do that, so I'm just going to overlay them, you can see that just do that again, sorry. So I won't overlay them because one of them vanishes. You can see that the difference between those 2 lines is precisely pi over 2. Okay, so what for any value of x, this is always true when we're talking about the inverse cos and inverse sine functions.